In this lecture, we're going to focus on primes and primes factorization. Previously, we have learned factors. Factors are, if we're given a number n, k is a factor of n, if and only if n divides k has remained 0. So n divides k equals something, let's say r remained 0. And we write k is a factor of n by k divides n. Of course, k is also known as a divisor n. Factor and divisor are equivalent. By this definition, we know that 1 is always a factor of n for any integer n. And n is always a factor of n. Because when I divide n by 1, remainder always 0. N by n, remainder is always 0. Now there are numbers that very special. The two only factors of itself are just 1 and n. And these numbers are known as primes. So let's put the prime definition here. Primes are numbers or integers only have two factors. One and itself. We focus on here, there are two factors. If there's only one factor, 1, then this is not a prime. So by this definition, 1 is not a prime because 1 only has one factor. It's not a prime. Very important. And we'll see that this is really for convenience. Later we'll learn that prime factorization, if we include 1 as a prime, then there will be, any number n can be written as 1 times n, also can be written as 1 times 1 times n, and can be written by 1 times 1 times 1 times n, because 1 times anything equals that thing. So by introducing this 1, then you can have many, many different ways of writing this way of factoring out, and that's not helpful. That does not add any value to this factorization framework. So really it's for convenience that we exclude 1 from this prime definition. 1 is not a prime. So by this definition, which numbers are primes? Let's see, 2 is a prime, 3 is a prime, 4 is not a prime because 4 has factors 1 to 4, 3 factors. 5 is a prime, 6 is not a prime because 6 equals 2 times 3, so it has factors more than 1 and 6, and 7 is a prime. So here I'm listing the first 10 factors. Here I'm listing the first 10 prime numbers, 7. And 9 is not a prime because 9 equals 3 times 3, so it has factors more than 1 and 9. Next prime number is 11, and then 13, and then 17, and then 19. We have 8. Let's see, what's the next prime number? 21 is not, because 21 equals 3 times 7. The next one is 23. And then 25 is not. 27 is not. The next one is 29. And so on. Now, these are the prime numbers. I'm listing the first 10 prime numbers. And the numbers are not primes are called composite numbers. These are the numbers having more than 2 factors. So a composite number will have a divisor k, which k divides n, and k is not 1 or n itself. These are composite numbers. Or you can think about using a complementary way. A number is not a prime number, is a composite number. Of course, we need to be a little bit careful about 1 or 0. I mean, in all these discussions, 0 is not even in consideration because we're talking about product of numbers, like, or a number is factoring into different numbers. 0 does not have a lot of meaning here. So composite numbers are numbers that are not primes. Let's say just bigger than or equal to 2 in positive integers, that if it's not a prime, then it is composite. So come back to the primes. The primes are very, very fascinating subject in mathematics. So far, people have not found a definite pattern of primes. If you see from here, you think that you found a pattern, you have to think again, because so far, none, including the best mathematicians of this current day or the past, including all the big names, Gauss, Euclid, Euler, none of them found a definite pattern of primes. And currently, there are still a lot of important and unresolved problems regarding primes. For example, I'm going to just give you one example of a very famous unsolved prime number problem, which is very easy to describe. You see from here, the primes, there are prime numbers that kind of are next to each other, 3 and 5. Now you say this is not really next to each other, the 4 is in between. But we know that even numbers other than 2 cannot be a prime number because even number has a factor 2. So even numbers other than 2 cannot be prime number. Actually, that's a small fact. For prime numbers, there's only one even number, which is 2. And that fact can be convenient in a lot of small math competition problems. So when I say 2 consecutive numbers in this sense, the 2 numbers closest for a prime number at least is a 2, right? So when the difference between 2 prime numbers is a 2, we call them a twin prime number. Twin prime numbers. So 3, 5 is a twin prime number. Or rather, it's called a pair of twin prime numbers. And then you see the next twin prime number is 5 and 7. 5, 7 is another twin prime number. And then you see 11 and 13. 11, 13 is another. The next one you see is 17, 19. 17, 19 is a pair of twin numbers. The next one, well, 23, no, the next one is actually 29, 31. So 29, 31 is a pair of twin prime numbers. Now, as you see that as numbers goes on, primes will appear less and less often. Why is that? Because, you see, I'm going to exclude all multiple 2's. They cannot be prime number. All multiple 3's cannot be prime number. All multiple 5's cannot be prime number. Multiple 7's cannot be prime number. So prime numbers will become less and less frequent. Spend a few minutes if you think that statement is a bit of puzzling. Try to convince yourself that prime numbers will become less and less frequent. But the interesting thing is, actually this twin prime number, it's always come about. It always come about. 31, the next one can be 30, 41, and 43. And the next one, 43, 45, 45, 47, 47, 49. They are all not. 51, no. 53, 57, 59, no. 59, 61 is another twin prime numbers. It seems that you can verify this until a very, very large number. Even though it becomes rarer and rarer, this twin prime number always appears. But no one knows this for sure. And this is so-called the twin prime number conjecture. It says, this conjecture says, there are infinite twin prime number pairs. And no one has proven it. And there is a big reward for anyone can prove that conjecture. So we have talked about prime numbers. There are still a lot of unresolved problems out there. But still, we know a lot about primes already. There are some simple facts I already mentioned. One is there's only one even prime number. Which is 2. Why there are no other even prime numbers? Because for any even number bigger than 2, you have a 2 as a factor. So by definition, prime number, you have 1 as a factor, itself as a factor, and a 2 as a factor. So that number cannot be a prime. Second, they are infinite. Prime numbers. Now, this fact is not very easy to prove. I'm going to show it in a different lecture. But this was proven a long time ago by Euler. He has a very nice proof about this fact. But this is no. There are infinite prime numbers. 3, let's see. If P is a prime number, a prime, then the greatest common factor between P and any number n can be either 1 or P. Cannot be anything else. If it's a P, then P is a factor of n. Otherwise, the greatest factor between P and n is 1. And when it's 1, this is also sometimes known as these two numbers are coprime. We are going to show this fact later, and we're going to use this fact a lot. So these are some of the things that we already know about prime numbers, and there are actually many, many things we already know about prime numbers, and we're going to talk about in later lectures. But first, let's talk about how we determine a number is a prime or not. So how do we determine a number? How to check a number is a prime. We don't have a better way other than trial and error. Remember, the definition of a prime is it only has two factors, 1 and in itself. So if we can find a factor other than 1 and itself, then we know that number is not a prime. So what we do is basically, given any number n, what we're going to try is just try all the prime numbers starting from 2. We'll do the following. Is 2, do a check. Check. Is 2 divides n. Is 3 divides n. Do we need to check is 4 divides n? No, because if 4 divides n, then 2 automatically divides n. So we don't need to check this. So by this, we know that we only need to check primes. Check only primes. All right, so that's kind of simplify the checking or reduce the time of checking a lot. So we need to check is 5 divides n and 7 divides n. We only need to check the prime numbers, right? And as long as we find 1, we stop, because that makes clear that n is not a prime number. Now the next question is, do we need to check the number until the largest number p, the largest number less than prime number p, which is less than n? Do we need to check all the way to that p? So for example, if I want to check if is 113, is 113 a prime number? Do we need to check all the way to the largest prime number less than 113, which is, I believe, is 109? I hope the 109 is a prime number. Do we need to check all the way to 109? Up to 109? The trick here is no, we only need to check a number far less than 109. In fact, we only need to check the prime number up to a p such that the p square, p times p, is bigger than equal to n. Or actually, we can check up to that point. Even before that, if the p squared is bigger than or equal to n, we stop. We don't even need to check. Okay? Before we prove that fact, I'm going to show you an example. So for example, the 113. So for 113, we're going to check, is 2 divides 113? No. Is 3 divides 113? No. And I hope you remember how you check if a number is a multiple of 3. You're just adding the digits to see if the sum is a multiple of 3. In this case, it's 5, so 5 is not a multiple of 3, so the original 113 is not a multiple of 3. Is 5 a divisor of 113? No. Is 7 a divisor of 113? No. Next, because 11, the next prime number is 11, 11 squared is bigger than equals 121, is bigger than 113. We don't even need to check the 11. So we are done. At this step, we are done. We know, we concluded that 113 is a prime number. So again, I want to make that statement. The statement says, to check a number is a prime or not, we only need to check if prime number p divides this number n. Okay, let's put more complete. If n is prime to check if n is prime, we only need to check if p divides n for p up to p squared bigger than or equal to n. Once we see that p squared bigger than or equal to n, we stop. So we only need to check a very small set of prime numbers. All right, how we prove this fact? It can be proven by the following. If n, let's see, if p divides n, a prime number p divides n, and that means n can be written as p times n. And if we focus on p is the smallest prime number, the smallest prime factor, then m is going to be a number is also divisor of n. Because m is also divisor of n, m is going to be bigger than or equal to p. Because p is the smallest prime factor, and m is also a factor of n, so m is going to be bigger than or equal to p. Because p is the smallest, so smallest is going to be less than or equal to any other factor, right? So n equals p times m is going to be bigger than or equal to p times p, because m is bigger than p, so p times m is going to be bigger than or equal to p times p equals p squared. So that means the p squared is going to be less than or equal to n. That's the proof. So if n is not a prime number, then the smallest prime factor of n is going to be having this property. P squared has to be less than or equal to n. So that means when I do the prime check, to check all the primes, if that prime is a factor of n, I only need to check all the way up to such a p squared less than or equal to n. So here we talk about primes, and we also talked about how we check if a number is a prime or not. And that's the end of this lecture.